So in our third lecture here in our chapter on electrochemistry, we move into some quantitative aspects of the process. So we talked about creating voltaic cells in our last lecture, and now we're actually going to be talking about how we calculate the value of that battery, if you will. What is the voltage that we're going to have with the creation of a certain voltaic cell? And then we're also going to think about, begin to start discussing how we create a relationship with delta G. So conceptually, we're going to be thinking about E representing an electron or a species affinity for electrons. So we call this the standard reduction potential. And remember that redox chemistries happen when someone wants to give up electrons. So they're going to then be a species that has a low affinity for electrons. They're willing to give them up. And somebody who wants to take on electrons. So we'd say that that species has a high affinity for electrons. So a really important concept that we're going to see here is if we want a spontaneous sort of voltaic cell, we have to have an E cell that is a positive value. So again, we're going to return to delta G a little bit at the end of this lecture and then mainly in our last lecture. But again, delta G is supposed to be negative if it's spontaneous. So again, delta G is negative if it's spontaneous. E cell is positive if it's spontaneous. So you know there's not a lot that I like to have be just memorization things in this course, but this is one of those things that we need to make sure we commit to memory, that spontaneous reactions have a negative delta G and then a positive E cell. So skills that we're going to practice today actually have to do with calculating what E cell would be for a certain voltaic cell using half cell values. And again, Appendix D is going to come into place with this. So a couple of homework problems that allow us to practice that, and we'll have about 3 problems that we work through in today's lecture. So when we talk about cell potential, again, that refers to the energy that's available in a voltaic cell to do the work, again, of moving a charge between electrodes and moving those electrons. So we refer to the standard cell potential as E cell or E naught cell, meaning that we're doing this at a specific temperature. So again, all components are going to be then in the standard states when we're looking at that little naught. So gases are going to be 1 atmosphere, concentrations of solutions are going to be 1 molar. And the reason for that is that just allows us to make sure that we compare apples to apples when we're using data from a table. So just like we saw with thermodynamic values, that naught means that, you know what, everybody's just got to be doing things under the same conditions so that we make sure that we're kind of keeping track of everything. So what we're going to see on, for example, Appendix D is what we call half cell potentials. So our E values for half cells. By convention, they're written as reduction reactions. So Appendix D is going to have what we call standard reduction potentials. So every half reaction is going to be written as a reduction reaction. So gaining of electrons on the left. Okay, and so what we'll see is we'll see a ranking of these depending on what their affinities are for electrons. So we're going to begin with kind of that zinc and copper half cell or voltaic cell that we diagrammed in our last class. So again, Appendix B is going to be really useful for this. This table that's within your textbook actually just has a brief listing of some of the standard reduction potentials. But what we can see here is the more positive a standard reduction potential is, the more that species is happy to gain electrons. So again, positive, remember we want E's to be positive. So the more that a half reaction has a positive E, the more it likes to be in that direction. So again, this reaction likes to be a reduction reaction. Fluorine likes to gain electrons and be reduced to fluoride. Let's go to the opposite end of the spectrum here, and we can see here that lithium cation really does not want to gain an electron. That's a very unfavorable standard reduction potential. And we've sort of got this arbitrary but defined 0 point. It's referred to as the standard hydrogen electrode, and that by definition is set at 0 for the standard reduction potentials. So things either are more happy to gain electrons or less happy to gain electrons as compared to this sort of standard reference point. So again, this is what we're going to see in Appendix B, but Appendix B is going to have a lot more below and a lot more above this standard reference point for hydrogen here. All right, so I'm going to give you a problem-solving strategy for calculating E cell. The reason that I do it this way is I think it's the easiest way. I think you're less likely to make mistakes. I think it's going to be something that has kind of relationships to other methods that we've learned. So I think in that way, I think it's the best way for teaching how to calculate E cell. So again, if you have another method that you've learned, maybe in another course, feel free to ignore everything that I'm saying. You can even skip this lecture if you feel comfortable with this. I just want you to use a method that works for you. I will say that the method that I'm going to teach you is somewhat different from what's taught in your book. We will always both arrive at the same answer, but again, it's a little bit different in terms of my strategy. Again, it's different from what is standard in the electrochemistry field. So sorry to my colleagues who are electrochemists. This is what I believe, though, to be the easiest way for students to learn this process and to arrive at the right answer. All right, so this is a slide you might want to kind of take a screen capture of, or again, just kind of take some notes on. These are the 4 steps that we are always going to use when we calculate E cell. So again, if we've got a voltaic cell, we want to figure out what the voltage of that cell is. Here are the steps that we'll use. The first thing is we want to make sure we think about the half reactions that are occurring. Again, for some problems, you may already know who's oxidized and reduced, again, what's going on in the anode and the cathode. If you don't know exactly what's going on, start out by writing both of the reactions as reduction half reactions. That'll allow us to find the values most easily on Appendix B. So again, even though we're writing them both as reduction half reactions, one of them is going to have to be flipped in order to have that be an oxidation reaction. So then what we're going to do is we're going to use Appendix D, and we're going to find the values, the standard reduction potentials for each of those half reactions. So again, we're going to use the value that we have directly as we get from the table, and we're going to write it as E reduction because Appendix B gives us standard reduction values. Now again, we're going to have one of the equations that we're going to need to flip. So again, for the one that we flip to make an oxidation reaction, we're going to take the negative of that value from Appendix D. And then we're going to write it again as E oxidation. Again, we're going to see in our step down here, if you don't know which one is reduction or oxidation, we're going to kind of talk about how you know which one that you'd flip. Okay, but then we need to think about scaling the equations. This has to do with sort of balancing the equations that we learned in our first lecture. We may have to have our equations be scaled so that the number of electrons that are lost equals the number of electrons that are gained. But this is really important. This is where this sort of differs a bit from what we learned with Hess's law. The E values do not change if we scale a reaction. They are what they are. They do not change if we need to scale up or down an equation. So the 4th step then is we're going to sum these equations. Electrons should cancel because we had to do this scaling up in this previous step. And what we do is we sum the E values. The sum of the E cell is going to be the standard reduction potential for our reduction reaction and then the potential for our oxidation reaction. Remembering that a spontaneous process has a positive E cell, if we don't know which is the oxidation and which is the reduction reaction, we are going to flip and reverse the sign of the reaction that allows us to have an overall positive delta E. So if this doesn't make sense in words right now with these steps, we're going to run through several examples today that will hopefully reinforce that concept. So let's sort of start with our first kind of process that we've spent a good bit of time learning about, this zinc copper voltaic cell. This is the one that we first learned how to diagram in our last lecture. And in it, we learned that the zinc compartment is going to be our anode, so that's where oxidation occurs. So I'm going to go ahead and write an oxidation reaction here. I'm going to show you on the next slide here, this would be a negative 0.76 if we saw it on Appendix D, because this reaction would be reversed. Okay, but this is the standard reduction or the standard potential that we have here for this oxidation reaction. For the copper, which we know is a reduction reaction, that value on the table is 0.74 volts. When we add both of these up, we can see that we get an overall positive E cell. So remember, E cell is really adding these two potentials together. And we get 0.76 plus 0.34 is positive 1.1 volts. Because that's a positive reaction or a positive E cell, that's a spontaneous reaction. So again, I'm going to show you here with Appendix D. So here again is the copper half cell reaction written as a reduction, right? So we can see we would use that directly as is, 0.34 there. If I try to find zinc on there, remembering that all of these are written as half cell reduction reactions. So all of these have electrons on the left. So in order to find the zinc piece, I have to find zinc 2 plus gaining 2 electrons to become zinc solid. Notice that the value for this is minus 0.76. But remember, we need to flip this reaction because we need to see it as an oxidation reaction. So when we flip that reaction, we need to change the sign from what we see on Appendix D. But that's what allows us overall to sum these together and have a spontaneous voltaic cell there. We have an E cell of positive 1.1 volts. All right. So let's talk a little bit more about this and do a couple problems on our own. Some of this stuff is going to be a review from what we talked about with diagramming our voltaic cells. Remembering when we have reduction occurring at the cathode, again, that's going to deplete the concentration of copper. And oxidation occurring at the anode means we're going to be making more zinc ions. We can again see that with our chemical equations here. We're going to be making zinc ions and using up copper ions. So again, concentration of copper is going to decrease, zinc is going to increase. So that's stuff that we already learned about actually when we diagrammed voltaic cells. So let's have you guys practice one here yourself, and then we're going to go through a couple of other examples here. So this first one says, we want to calculate E cell when we have a spontaneous process in a tin silver voltaic cell. And again, they didn't give us any other information to say that we've got tin and silver. Now, if this was a problem we did in our last lecture, we would have said which electrode was positive, and that would have told us which was the cathode, or which electrode was negative, and that would have told us which was the anode. We don't know that here, but we have Appendix D. So I want you to think about this. I'm going to give you a few clues, and I want you to try this on your own. Write both of these reactions as reduction reactions, and then figure out which one you'd want to flip in order to have an overall E cell that's positive. And then the one that you use as is, that's going to be your cathode. The one that you need to flip, that's going to be your anode, your oxidation. So pause the video for a second and see if you can write down both of these reactions, write them both down as reduction reactions, and then look at Appendix D and see if you can figure out which one we might need to flip. All right, so here's the data from Appendix D. We can see if we write these both down as reduction half reactions, we're going to have the tin reaction having a negative standard reduction potential, and the silver reaction having a positive one. So now again, think about which one of these reactions do we want to flip in order for us to have a positive E cell, and then see, do we need to scale either of these reactions to make sure that we'd have an overall balanced redox reaction? So think about that, try to figure out how you'd get a net overall reaction, and then think about what that means is going to go into our voltaic cell diagram here. So first, let's just try figuring out what our overall E cell is going to be for this balanced chemical redox reaction. All right, so hopefully you quickly recognize that this is going to be the reaction that we need to flip. That's the one that has the most negative standard reduction potential, E reduction. So we're going to flip this guy. And remember, when we flip this reaction, we need to change the sign on E, and we make it an oxidation. So again, we make this an oxidation reduction or oxidation potential here, which means we change the sign. And then we actually need to leave the silver one the way it is, but we need to scale it. So we're going to scale everything up by 2 so that we have the 2 electrons in our reduction reaction that we need to cancel. So again, everything gets scaled up by 2, but we do not change the value of our standard reduction potential. That stays as is, as positive 0.8 volts. So again, we're going to sum these up to get our overall balanced redox reaction, making sure, again, our electrons cancel. That's skills that we learned in our first lecture. And then E cell is equal to the standard reduction potential plus the reduction potential that we've made into an oxidation potential. So we're going to add both of those together, and we get 0.94 volts. So what I want you to do now that we know all of this information, see if you can practice a skill from last lecture and take this information and map it onto a voltaic cell diagram. So go ahead and try that. Pause the video and see if you can figure out that solution. All right, so we knew that we were going to have our tin be our oxidation reaction, so that's going to be our anode. So we're going to have a tin electrode, and we're going to be generating tin ions in solution. So our silver kind of chemistry is going to be our cathode half cell. That's where reduction's occurring. So we've got a silver electrode. Both our electrodes are active in this voltaic cell. And we're going to have to make sure that we have silver ions in solution, because those silver ions that are in solution are going to be what are used to get reduced. Again, anions are going to flow to the anode. Cathode is going to be where cations migrate to in our salt bridge. But now we can fill in this last little piece. We know that the value of this voltaic cell is 0.94 volts. Okay, so kind of pulling in skills from all three lectures here: balancing redox equations, diagramming voltaic cells, and now importantly, figuring out the quantitative value of those voltaic cells. All right, so you remember when we were learning about acid and base chemistry and we learned about acids and bases reacting, we always had strong acids and strong bases react to make weaker acids and weaker bases, right? That's how chemistry happens. Things that are more reactive react to become less reactive. Things that are strong acids and bases react to become weak acids and bases. The same is true here when we think about having spontaneous redox reactions. Things that are stronger oxidizing or reducing agents become weaker, okay? So that's going to be kind of a general rule that we have here. Keep in mind too, let me flip back here for a second. If we actually wanted to have this reaction run in this direction, we could do that, but we would have to put in 0.94 volts of energy. Run in this direction, we get 0.94 volts of energy out. Running it in this direction, we'd have to actually put in 0.94 volts of energy. Okay, so the same is true here. We're going to have chemistry happen to generate weaker species. Okay, so this next problem is going to actually get us to start thinking about identifying the strength, the relative strength of oxidizing and reducing agents. Remembering that something that is an oxidizing agent is itself reduced. Something that is a reducing agent is itself oxidized. All right, so again, one more quick problem here to sort of calculate voltaic cell sort of information using Appendix D, but this one's a little bit different. Do you remember sometimes when we did stuff with Hess's law, sometimes we'd have to look up everything, or if we did standard heats of formation, sometimes we'd have to look up everything on Appendix B, and then we'd sum it up all to make an overall delta H of reaction, right? But we had a few problems where maybe we were given delta H of reaction and we had to find the delta H of formation for one of the species that was there. So for example, this problem that we did here, we had to calculate what the overall was, and we had to look up each of the individual pieces. Can you see that for this problem, they've actually given us the overall, and they've given us one of the half cell. Now, actually, if you actually looked this up on Appendix D, you'd actually see that it's the same value. But they want us to calculate the E for bromine. Okay, so now we have to figure out that unknown. So see if you can figure out and sort of work through this different permutation, if you will, of sort of our E cell reactions, and see if you can figure out how to calculate E for bromine. Pause the video and try to sort of work through it yourself, or again, let the video play if you kind of want to just see a worked out solution. As a hint, the first thing that I want you to do is try to split up this reaction into its corresponding two half reactions. Okay, so if we split this up into its corresponding half reactions, we're going to have here a reduction reaction here, right? We've got bromine going to bromide, which means it's got to gain electrons. We've got zinc going to zinc 2+, that's our oxidation reaction. Don't need to do any scaling here because we've got 2 electrons that are being traded there. They told us that the E for zinc, again, was going to be negative 0.76 if it was a reduction potential, right? And again, if we looked it up on Appendix D, we would see this value, but we're making it into an oxidation half reaction, which means we're going to change the sign, flip the sign. They told us what E cell was. E cell is E reduction plus E oxidation. So again, we know the oxidation piece and we know what they sum up to, but we don't know this piece. So see if you can finish out this problem to figure out what this missing piece is. All right, pretty straightforward here. We just sum up everything, right? Sum up everything, we get to our overall equation. Sum up everything, we know that everything needs to sum up to positive 1.83. So if we need to sum up to positive 1.83 and we already have 0.76, just a little bit of algebra will allow us to figure out what this guy is. So again, positive 1.83 equals our standard reduction potential plus the oxidation potential, which we already know. And so just solving again for this unknown tells us that the E reduction for bromine is going to be 1.07 volts. All right, so last problem to work through here. This is actually going to be kind of 4 problems in one, because first we're going to actually calculate or think about the relative strengths of each of these as oxidizing and reducing agents, and we'll talk about how to do that. That's going to be kind of like a part 1 sort of problem. You know, who is the strongest oxidizing agent? Who's the weakest reducing agent? And so forth. And then we're going to label these reactions A, B, and C. And we're going to look at the different combinations we can have for creating different half cells. So just to kind of set this up, we can have an A-B reaction, we can have a B-C combination, or we can have an A-C combination. So we're going to create half cells by mixing those different sort of possibilities together and see what we come up with. So it's kind of, 3 problems in one in that regard. But the first thing that we're going to do is think about sort of tackling this question. Who is the strongest oxidizing agent? Who's the strongest reducing agent? So I'm going to walk you through this problem because it might be a little bit difficult to just kind of throw at you. So see if this makes sense here. Right now, I have identified in green here things that are reduced, right? These are species that are reduced, right? Because they're on the left side of a reaction that's gaining electrons. So these are things that are being reduced, which means they are oxidizing agents. These guys over here are species that have become reduced. So again, if we're thinking about the reaction going in the opposite direction, these are going to be species that maybe likes to be oxidized, okay? Because if we're going to go in this direction, that means that we're going to be giving up electrons. So remember, anything that's gaining electrons is something that's being reduced. Anything that would be giving up electrons is something that's being oxidized. Okay, so we've got 6 things here that we've got to rank. The things that are in green are the things that are being reduced. The things that are in red are the things that are going to be oxidized if we consider the reverse reaction. Okay, so hopefully everybody's okay with me. What we need to do now is recognize that there's sort of a ranking here. Remember, the more positive an E value is, the more that reaction likes to go in that direction as written. So we can kind of see a ranking here. This is sort of the most positive E, then we've got this guy, then we've got this guy. So what this means is MnO2 most likes to gain electrons. So again, if we want to think about the strongest oxidizing agent, that means it's the guy that most likes to be reduced and gain electrons. Based on the standard reduction potential, it's this guy right here. So MnO2 is the strongest oxidizing agent. Then the next one kind of ranking here is this first reaction. So NO3 is going to be the next guy in terms of liking to gain electrons. And what we actually really have here, this guy really doesn't like to gain electrons. We've got a standard reduction potential that's negative. So in terms of ranking these three, here's the order that we'd put them in. Most likes to gain electrons, still likes to gain electrons, doesn't want to gain electrons at all. Now let's look at the flip side. Let's look at these in terms of oxidation reactions, remembering that something that is going to be oxidized is a reducing agent. So in this case, we want to think about, again, looking at if these were positive E cell values, which of these most likes to give up electrons, right? This is going to be the most positive E going in that direction, right? So this guy most likes to give up electrons. And if we actually were to look at E's for these two reactions, again, they'd be flipped if we're looking at them as oxidation reactions. Then going in order, this guy's going to be next, and then this guy. So N2H5 plus most likes to give up electrons, then NO, and then Mn2 plus. So again, that's a little bit of a kind of a difficult concept to think about, but again, a really important skill. You're going to see questions where you're going to sort of rank or see a laundry list of things, and you're going to be asked, who is the strongest oxidizing agent or the weakest reducing agent? Okay. All right. So again, if we want to think about sort of putting these reactions together, right? And I'm going to label them A, B, and C here. I'm going to kind of put that back over here. We've got A, B, and C that we have here. If we're thinking about kind of making spontaneous reactions, hopefully it makes sense that we're never going to have a situation where this guy becomes a flipped reaction. We're never actually going to take C and flip it, because that would make this being minus 1.23. And neither of these reactions could compensate for that. So this reaction is always going to be in this direction, okay? We can't flip it and then compensate for that negative 1.23 volts and end up with a positive E cell, okay? So keep that in mind. What we're going to run through now is our different combinations. All right, so let's think about our A-B combo. Okay, so this was the reaction that I labeled A and B over here. So I've just sort of rewritten them here. I want you guys to put these reactions together so that we have a positive E cell and tell me what the overall chemistry is going to be for that reaction. So again, I want you to pause the video and see if you can figure out how would we create and what would the voltage be on a spontaneous reaction for these two processes. All right, so again, bringing in some stuff that we actually had to learn in our first lecture here. We also have to make sure that we're scaling things appropriately with the right numbers of electrons. Notice that's not going to change what we have over here. But hopefully it makes sense to everybody that this is the reaction we want to flip. Because flipping this and making it negative 0.96, that's not going to help us at all to have a positive E cell. But flipping this guy certainly will help. So this is the guy that needs to be flipped, and we actually need to scale these quite a bit in order to have those electrons cancel. So the first reaction needs to be scaled up fourfold, remembering we do not scale the standard reduction potential. Our second reaction gets flipped, so it becomes an oxidation reaction, so we change the sign on that value, and then we need to scale that guy by threefold. That allows 12 electrons to be exchanged between these guys. And then when we allow those electrons to cancel and we reconcile protons being on both sides here, we sum them up to get this overall kind of reaction. Pretty messy reaction, lots that we have there. But again, E cell is going to be the sum of these two kind of potentials that we have here, an oxidation and a reduction potential. Overall, this is going to be positive 1.19 volts. That's a spontaneous reaction, positive E cell. All right, I want you guys now to try the A-C combo. See if you can figure out who gets flipped here, How do we scale? What's our overall final redox reaction? And what's the value of that E cell? So pause the video, try to work through this one. All right, remember when we talked about this C reaction, we said this guy's never going to be flipped because we couldn't compensate for that negative 1.23 volts. So this is the guy that needs to flip up here. So again, we're going to flip this. And again, we note that we need to flip that one because that's what allows us to have a positive E cell. So again, flipping this guy, we need to scale the first reaction up by 2, the second one up by 3. Remembering we do not scale the potential values here. Got to reconcile protons and water that we have here. Here is the final balanced chemical reaction. So again, we're practicing some skills from our first lecture there in balancing redox reactions. Bringing in kind of the new component here, we're going to add up the accompanying potentials for the reduction and oxidation half cells. And again, this time we have a negative value that we have here. But again, adding a negative value is like subtracting it, so we end up with positive 0.27 volts. All right, last combination to try. And again, if you haven't gotten the first two, hopefully you feel comfortable enough to take a stab at this one. Pause the video and try to work through the BC combo with these two reactions. Figure out what the overall balanced chemical redox reaction is, and then what E cell would be for this voltaic cell. All right, again, this is the one that needs to flip. We cannot flip. We're never going to see this guy get flipped. So flipping the first reaction, and again, we don't need to scale that first one. We just flip it here. And then we do need to scale the bottom reaction by 2-fold so that we have an even exchange of electrons there. Kind of reconciling things that appear on both sides to balance our chemical equation. Here's our net final balanced chemical equation. Adding our oxidation and reduction potentials here gives us an overall E cell of positive 1.46 volts. Now, one of the things I kind of want to highlight here as we kind of wrap up here is this is what we might call the winningest combination. Looking back, this one has the most positive E cell, 1.46, 0.27, and 1.19. So that was the most favorable E cell. Okay, not surprisingly, it had the strongest reducing agent paired with the strongest oxidizing agent. So look here. Remember these two guys, N2H5 plus and MnO2. I'm going to flip back to when we figured out who was the strongest reducing agent and the strongest oxidizing agent. So the strongest reducing agent was N2H5. The strongest oxidizing agent was MnO2. So it's no surprise that mixing those strong combinations would give us the battery, if you will, that had the strongest, highest voltage. All right, so we've kind of built on skills from Lecture 1 with balancing redox equations, Lecture 2 with kind of thinking about voltaic cells, and now putting a quantitative piece to it. So again, calculating E cell. So again, here's some kind of steps to go through to calculate E cell. And again, understanding that a large positive E cell is going to be sort of the most favorable process. So, we're not going to get into delta G yet, but we sort of hinted at delta G at the beginning. Delta G being a spontaneous reaction is going to be negative. Delta E being a spontaneous reaction is going to be positive. In our next lecture, we're going to pull this all together and we're going to learn an equation that allows us to relate delta G and E cell.